let's jump right into this. Today, we're going on a bit of a journey into a world that's literally hiding in plain sight. We're diving deep into the surprisingly complex microscopic universe hidden inside a simple component catalog. Specifically, we're cracking open the Vitalconn USB Type-C connector catalog to deconstruct the iceberg of modern hardware design.
I mean, think about this for a second. Have you ever actually looked closely at the bottom of your phone or maybe the side of your laptop? You see that little oval USB-C port? We use them every single day, right? We just plug them in, wait for the click, and don't give it a second thought. But beneath that totally uniform, universal exterior lies a staggering array of engineering choices. Choices that dictate exactly how thin your device can be, how fast it charges, and honestly, whether it survives getting dropped off your nightstand.
So to make sense of all this invisible architecture, here is our roadmap for today's explainer. First, the USB-C illusion. Second, decoding SMT and DIP. Third, the syncing height factor. Fourth, exploring pin counts. And finally, engineering the perfect fit. Okay, Section 1, the USB-C illusion. It's time to realize that what you see on the outside of your device is definitely not what you get on the inside. We all recognize that familiar facade. It looks standard, it looks simple, but that outer shell? It's just the tip of the engineering iceberg. A manufacturer can't just call up Vitalconn and say, hey, send me 1,000,000 USB ports. No way. They have to navigate an incredibly specific matrix of physical dimensions and electrical capabilities to get exactly what they need. When hardware engineers flip through this catalog, they aren't looking at pretty pictures. They're looking at shorthand strings of letters and numbers representing super precise specs. I mean, it looks like a foreign language, doesn't it? Well, today we are going to translate this together into conversational English and unlock the secrets of how our devices are actually put together.
Which brings us to Section 2, decoding SMT and DIP. Let's demystify two of the most absolutely crucial acronyms in circuit board manufacturing. SMT stands for Surface Mount Technology, and it's exactly what it sounds like. The component's terminals are pasted flat right onto the surface of the printed circuit board. DIP, on the other hand, is Dual Inline Package. With DIP, the connector actually has tiny pins that plunge straight through holes drilled into the circuit board itself. So why does this matter? Well, SMT saves a massive amount of space on the board, but DIP provides incredibly strong structural integrity. When you violently yank your charging cord out of your phone in a rush, those DIP pins are often the only thing stopping the whole port from ripping right off the motherboard. You can really see the sheer physical difference between these methods here. You've got a vertical mount designed to stand straight up with pins plunging through the board, compared to a horizontal model designed to be pasted flat. Engineers will actually frequently mix these. They might use SMT for the delicate internal data pins to save space, but then use DIP for the tough outer shell to make sure your port doesn't just snap under daily stress. Moving right along to Section 3, the syncing height factor. Have you ever wondered how your smartphone or your ultra-thin tablet gets so impossibly slim? A standard USB-C port sitting directly on top of a circuit board is, frankly, just too tall for modern devices. The clever workaround is something called a syncing height design. Engineers literally cut a precise notch out of the circuit board and mount the connector inside that cutout. It lets the belly of the connector sink below the board surface, lowering the entire profile of the hardware. And Vitalconn provides an overwhelming array of options just for these 16-pin syncing models. Just look at the catalog data. It reveals syncing heights of exactly 0.8 millimeters, 1.0, 1.6, all the way to 2.1 millimeters. Notice that contact height column. That tells the engineer exactly where the center of the internal tongue sits relative to the board. In some models, like that 1.6 millimeter variant, the center is actually negative 0.02 millimeters, meaning the very center of the plug is essentially perfectly flush with the board itself. That is wild. Consider a contact height of just 0.58 millimeters. Let that sink in. That is literally less than the thickness of a standard credit card. These are the microscopic contact heights that hardware engineers are agonizing over every single day. Just to make your device a fraction of a millimeter thinner, they have to source a port with exactly this level of extreme precision. The physical manifestation of these numbers reveals incredibly subtle visual differences.
the underbelly of a connector with a 0.8 millimeter sink versus a 1.0 millimeter sink, they might look totally identical to the naked eye, but to a manufacturer designing a tightly packed smartphone chassis, these subtle variations in metal shielding and board cutouts are literally the difference between a product that snaps perfectly together on the assembly line and one that utterly fails.
Let's transition to Section 4, Exploring Pin Counts. So we've talked about how these ports attach to the board. Now let's talk about the data and power highways hidden inside them. A fully featured USB-C connector has 24 pins, which allows for incredibly fast data transfer and massive power delivery. But you don't always need all 24. If you're building, say, a cheap Bluetooth speaker that just needs to charge, 24 pins is total overkill. So Vitalconn offers variations. You have 16-pin models that drop some high-speed data lanes, 14-pin and 12-pin models that strip things down even further. It is all about giving engineers exactly what they need without wasting a single millimeter of internal real estate. In a fully populated 24-pin model, you can see just how insanely densely packed those tiny golden terminals are. Every single one of those microscopic pins has to be soldered flawlessly to the motherboard during mass production. It really kind of grounds you when you realize that every time you casually jam your charger in the dark, this complex, highly sensitive architecture is what you're actually interacting with. And engineers can combine these techniques to build even more complex hybrid solutions. They might choose a front DIP and rear SMT configuration, meaning the front of the shell plunges through the board for strength, while the rear pins paste flat for easy soldering. Or actually, they can choose an entirely different approach, the edge straddle model. And that brings us perfectly to our final section, engineering the perfect fit. The straddle model is an absolutely brilliant piece of engineering. Instead of sitting on top of the board or sinking into a hole in the board, the connector literally has a mouth that clamps onto the very edge of the printed circuit board. Vitalconn offers these straddle variants tailored to exact board thicknesses, 0.80, 1.00, or 1.20 millimeters. It completely saves critical surface space by pushing the port right out to the absolute perimeter of the device. So the really crucial point here is the staggering compactness of these parts. 10.45 millimeters. That is the total length of one of their high-performance 24-pin straddle models. That length contains the outer shielding, the grounding, the internal tongue, and all 24 individual data and power connections. The whole shebang, housed in a space roughly the width of your fingernail. To summarize the vast solutions required by the tech industry, just consider this complete arsenal we've uncovered from a single catalog. Vertical mounts for standing docks, straddle clamps to bite onto board edges, sinking variations to shave millimeters off a smartphone's thickness, horizontal pastes, dual row configurations. Engineers don't just pick a USB-C port. They carefully select a highly specific weapon from this arsenal to solve their precise spatial and electrical problems. Which leaves us with this final thought. We interact with these connectors every single day, entirely blind to the intense, calculated engineering that makes them work flawlessly. The next time you plug in your phone, your laptop, or your headphones, take a second, look at that tiny port. Will you wonder which microscopic architecture is hidden inside? Is it SMT or DIP? Is it straddling the board or sinking right into it? Thank you so much for exploring this hidden world with me. Until our next explainer, stay curious.